we also have a new coherent free space optical channel. I show it here, so you can see all the related parameters. Okay, so atmospheric turbulence here will cause random now phase and amplitude fluctuations at the same time, and that will obviously degrade the signal. So at the receiver, the optical field will show a speckle-like pattern due to these distortions. So in this module, we model it as multiple coherent cells, and each having a constant phase and amplitude, but they're independent from each other. And each cell contributes to a complex phasor to the overall signal. In addition, we can have also adaptive optics for the case of compensate for phase distortion in the free space optic systems. And this is typically done by adjusting optical elements such as mirrors in order to correct for wavefront distortions, which are caused by the atmospheric turbulence. So we have two new demos. So the second one actually will give you more information about the model. And the first one is regarding this one here. This is for single carrier 16 QAM transmission of a FSO channel between a low Earth orbit satellite and an optical ground station. And yeah, so we have selected the link type here to be downlink, but you can also, it also works for uplink or horizontal. And the adaptive optics here are used through the Zernike model decomposition. So essentially through this parameter here. So we have set it in the global parameters as number 3 by default. And this one, each mode for that actually represent a different type of distortion, such as tilt. And we need to compensate for these modes in order to get less errors and have a reduction of the phase distortions. Check also in the model, you can have different scintillation models. For example, you can have behavioral, where you can have the expression through the rate of variance, or the atmospheric coherence width, which is related to the Frid's parameter. And you can also have attenuation only or through the analytical model. And you can also have different expressions from the CN squared scintillation profile model. So here we have user defined, but you can select through standards. For example, SLC refers to the laser, to the satellite laser communication, or the FGL AMOS model. This is related to the Air Force Geophysics Laboratory atmospheric model for optical systems. And yes, now regarding the demo, you can see that we can use a coherent system with existing hardware, existing DSP. So we can use the same DSP we can use for fiber transmission communications. And yeah, so for this purpose, we have set to some line with the transmitter and the receiver local oscillator and some offset. And we also include adaptive equalization in single polarization here for channel estimation for the 16 QAM channel. And in this demonstration, also we use this module to have more statistics. So we have an average of 10 runs here. Okay, so if we check the sweep, and I will run it, so we will sweep now and check through the Zernike mode decomposition. So when we run through 0, so that will be no compensation, but then we have set to some higher values, such as the number 3 actually represent tilt compensation, while the number 6 will represent astigmatism compensation. And we can have much more modes, for example, 20 or even more. So yeah, so running this module now here, we can see also, I have set on the histogram for the power distribution related to the number of events and the normalized power. So you can see the clear receive constellation diagram, and here we sweep the symbol error rate versus the null Zernike modes, and it is named null because null actually is the solution to the Zernike polynomials. And we can see by compensating this, we further improve the symbol error ratio. So the constellation diagram looks like this. This is from the CAT Constellation Analyzer Tool module, which has been placed here. And this is the evidence of the distorted constellations through the transmitted laser line width and the phase distortion, and the related turbulent channel, turbulent coherent channel. And here also we can see the transmit and receive the different power levels. We can see the significant drop due to attenuation. Okay, so one final part to show here is that you can have also the message log. And now I'm going to do a single run. And through the message log, you will have also the possibility to see over here in the message log the outputs of different parameters. So, for example, SI is for scintillation index, which is equal to rate of variance, or alpha is the average attenuation, and so on. But just remember, this has to be set also in the input name here.